Hi, and welcome back to our AP Chemistry Flipped Classroom, where we are continuing our discussion of gas laws today. So we've already learned about Charles' law, so we can relate volume and temperature. We've learned Boyle's law, so we can relate pressure and volume. And we've learned Gay-Lussac's law, so we can relate pressure and temperature. So we're going to add three more laws today. And that almost rounds out all the laws, or at least the mathematical laws that we need to know about gases. So let's go ahead and jump in with the first of the three that we're going to learn this afternoon, and that's called the combined gas law. So the combined gas law takes the three laws that we've already learned, Boyle's law, Charles' law, and Gay-Lussac's law. Those laws relate pressure, volume, and temperature. Notice that they relate pressure, volume, and temperature of a fixed amount of gas. And in those three laws, we were varying one of our parameters and seeing its effect on a second parameter while we held a third one constant. So the combined gas law allows us to change two of those variables and see what happens to the third one. And it literally just combines the three laws you already know. And so the combined gas law is pressure 1 times volume 1 divided by temperature 1 is equal to pressure 2 times volume 2 divided by temperature 2. So really just takes those same three laws that you already know and combines them into one. And the nice thing about the combined gas law is we can use it for any of those variables, because even if we're holding one constant, then it just cancels out because it's on both sides of the equation. So that's the combined gas law, very simple. And so let's move on to Avogadro's law. And you might remember Avogadro, our friend from the mole, and you might remember Avogadro's number. And Avogadro's law relates moles and volume. And Avogadro's law says that the volume of a gas is directly proportional to the number of moles, providing that temperature and pressure remain constant. So now, instead of holding the number of molecules constant, we're holding the temperature and pressure constant and varying only volume. You could also look at an extension of Avogadro's law and say that if we hold temperature and volume constant, then pressure is directly proportional to the number of moles. But that's just kind of an extension of Avogadro's law. And so Avogadro's law we express mathematically as volume 1 over N1, number of moles, is equal to volume 2 over N2. So V1 over N1 equals V2 over N2. And then the third and final law that we're going to learn today is Dalton's law of partial pressures. And Dalton's law of partial pressures says that if you have a mixture of gases in a container, the total pressure in the container is equal to the partial pressures of each of the individual gases in the container. And that just makes sense. If you think about the kinetic molecular theory and the definition of pressure, this is totally logical. The gas molecules of each gas exert pressure on the container walls independently of each other. And so the total pressure is the sum of the pressures exerted by each gas. And we use this most often in chemistry when we're calculating the pressure of gases collected over water. So one of the common experiments that we do, or one of the things that we do very commonly in the lab, is that if we want to measure the amount of gas that is created in a reaction, it's hard to measure gas. And so we measure it by collecting it over water. So you can see in my little experimental setup here that I have a tube filled with water and a container filled with water. And then I have a pipe or a tubing leading to that test tube or containing vessel. And so initially this is full of water and there's water here. As our reaction proceeds and gas bubbles in, then it fills this tube, and that's closed on the top so it can't escape. And so when the level of the liquid inside and outside is the same, the pressures inside and outside are the same. This is kind of like a barometer backwards, right? And so usually this is an instrument called a eudiometer, which has markings on the side so we can measure the volume that is produced. But what's in there isn't just the gas that I want. What's in here, because this is collected over water, there's going to be the gas that was produced, but there's also going to be some water vapor because we're in contact with this water surface down here. So in a closed system, we're always going to have some water pressure if we have, or some vapor pressure from the water if we're in contact with water. And so we can look those up. We can look up how much equilibrium vapor pressure of water is at a particular temperature. And so we can learn what the equilibrium vapor pressure of that water is. And so that allows us essentially to subtract out the pressure from the water to find the pressure from the gas itself. And we'll use that later on in something called the ideal gas law to determine the number of moles of gas that was produced. So here's a practice problem with that type of a problem. So we collect our gas sample over water. Our temperature is 35 degrees Celsius, and the barometric pressure reading is 742 torr. So we know from our experimental design here that when the level of the liquid inside the tube and the level of the liquid outside the tube are the same, then the pressure inside and the pressure outside are the same. And so this barometric pressure is the pressure inside the tube. But remember, the pressure inside that eudiometer is coming from two things. It's coming from the gas that I collected, and it's coming from the vapor pressure of water. And so we look up our tables of vapor pressure of water, and at 35 degrees Celsius, we find that the vapor pressure of water is 42.2 torr. And so I know that the total pressure is the atmospheric pressure. I know also that the total pressure is the pressure from the water plus the pressure from the gas that I collected. And so I just substitute in the partial pressure of the water, and I'm able to determine that the pressure of the gas is 7.00 times 10 to the second torr, or 700 torr. But we need to express that it has three significant figures, so we change that into scientific notation. So that's an example of Dalton's law of partial pressures. Let's take a look at a problem that uses the combined gas law. So if we have 5 liters of gas that contains 0.965 moles of gas, and we increase the amount of gas to 1.80 moles, and we want to know what the new volume is. Well, now we're going to go to Avogadro's law. And so that's V1 over N1 equals V2 over N2. And we're just going to substitute in those values. So my initial volume was this 5 liters. My initial number of moles was 0.965. My new number of moles is 1.80. And now I want to find my new volume. So I'm going to substitute in the 5, the 0.965, and the 1.8. And I'm going to solve for volume. And I'm going to get that the new volume is 9.33 liters. And our final practice problem is with our combined gas law. So here we have an unknown volume of gas. So B is a question at a pressure of 0.50 atmospheres and a temperature of 325 Kelvin. So if I raise the pressure to 1.2 atmospheres, decrease the temperature to 320 Kelvin, and measure the final volume to be 48 liters, what was the initial volume of the gas? So here's our combined gas law, P1 V1 over T1 equals P2 V2 over T2. And now I'm just going to plug in the values that are in my problem. 0.50 atmospheres goes with the unknown volume and the temperature of 325 Kelvin. And then my new pressure is 1.25 atmospheres, my new volume is 48 liters, and my new temperature is 320 Kelvin. And now I'm just solving for V, and I find that my new volume is 120 liters. So 3 new laws, pretty simple, just algebra applications, just like the other 3 laws. As always, I look forward to seeing you in class and answering any questions. See you soon.